So following on from the previous two videos, we are sliding x back and forth here, and we're trying to, as we slide x back and forth here, we are trying to make y the minimum. We are trying to get y to be at its lowest point. So we are sliding x back and forth here. Don't forget we've introduced capital L for the total length of our string. So hang on. So we are sliding x back and forth, and we are trying to minimize y, and then there's the capital L is the length of our string here. So let's look what happens as we slide x back and forth. As we slide x back and forth, y would be a function of x. So when later on, when we use implicit differentiation, if you try and differentiate y, you need to stick dy by dx into here. Okay. So now hang on. As we slide back and forth here, the length of our string, will this L here, the length of our string will always be the same. It's not a function of x. L is not a function of x, because as we slide back and forth here, the length of the string doesn't vary. It will stay the same at, let's say, if the length is 12, it will always stay at 12 meters. But the point here is that L is not a function of x. Okay, so looking at our formula here, L is not a function of x, y is a function of x. So when we come to use implicit differentiation, we've got to stick dy by dx in here. Let's look at A here. Okay, so back to this point here. A here, as we slide x back and forth, A will always stay the same. A is not a function of x. A will always stay the same, and that the same goes with B. When you as you slide x back and forth, B will always stay the same. B is not a function of x. The only thing that's a function of x is y. As you slide x back and forth, the height will vary. The height will vary. So when you use implicit differentiation here, this here is a constant, B here is a constant, A here is a constant, y here is y is a function of x. Okay, so this is a constraint here. Remember, we place this condition upon us where this length plus this length here, plus this length here, which is this bit here, must always be the length of our string. So we place this constraint upon us here. So now we can use implicit differentiation. But before we do that, let's look at what happens when you try and plot if you get a graph plotter and try and draw this graph here. Make something up. Let's say put 12 into here to be the length of our string, and then put let's say 10 into here, and let's say put 2 into here. So what we've got here is this. Hang on. So put some random numbers in here just to have a sense of what's going on. Put 10 into the A, put 2 into the B, and put 12 into here. So what that means is that the length of our string here is 12, and the point A here will always be at the origin. Point B here is 10, 2. Okay, so this is our point B here. You see, as and the length of the string here is 12. Okay, so what that means is, remember, our domain is really between 0, so we don't really care about this, and we don't care anything beyond this. So we can pretty much forget about this. Okay, and because gravity is always downwards here, well, we're going to assume that we're not going to have any negative gravity. So let's forget about this. Okay, so we don't care about anything in this region. We don't care about anything in this region. We are going to assume that we're not going to have any negative gravity. So this is just a bit that we're interested in. Okay, so hang on. So what that means is that if you put a snooker ball, if you hook the snooker ball right here, okay, it will just slide down here, and it will settle at the point where y will be at its lowest point, maybe somewhere around here. So we basically, looking at this here, we will need to differentiate this, and then try and locate the point where dy by dx will be 0. That's this turning point here. Somewhere along here, dy by, well, looking at this equation here. If you plot this, it will give you this. Okay, but we want to find out the lowest points. So we need to differentiate. We need to differentiate this, and then try and find out where the gradient will be 0. That will then give us the point where y will be at its lowest. Okay, so in the next video we're going to try and differentiate.